In this video, I'll show you how to solve the ALEKS problem called Solving Combustion Thermochemistry Problems. There are 3 different versions of this problem, and I've made separate videos describing how to solve each one of the different versions. This particular problem is going to be a description of how to solve the problem that pertains to balloons, blowing up balloons. You've got a data table that looks like that. However, if you are working on this version of the problem that's asking you to calculate the number of canisters needed for a wilderness expedition, then I want you to look for my video called Solving Combustion Thermochemistry Problems Part 2. And if you are working on this version of the problem and it's having you burn something in a constant pressure calorimeter, that tutorial is under Solving Combustion Thermochemistry Problems Part 1. So for this particular version of the problem, we are being asked to determine how many balloons can be blown up by a specific quantity of fuel. The quantity of the fuel is definitely going to vary from one problem to the next, and the fuel may vary as well. So what we're going to be doing in this situation is taking this fuel and combusting it or burning it as a source of heat, and that heat is going to be used to blow up the balloons. The first thing that we need to do is write and balance a chemical equation that describes the combustion of whatever fuel you have in your problem. So whatever fuel has been given to you in your problem, write that out. The combustion reaction means that we're going to be reacting that fuel with oxygen, O2. The products of the combustion reaction are always CO2 and H2O. So no matter what fuel you have, your products are CO2 and H2O, and then you need to balance that equation. It's super important that you get this equation correctly balanced. If the equation is not balanced correctly, you're definitely going to get the problem wrong. So don't just copy my stoichiometric coefficients unless you also happen to have propane, C3H8. If you have C3H6, or if you have some other sort of fuel, your coefficients are going to be different. So this reaction, when it this reaction generates heat, and that heat is going to be used to blow up the balloons. So we need to figure out how much heat is actually being evolved when this reaction runs. And the way that we're going to calculate the heat, there's a few different ways that you can calculate the heat of a reaction, but for this particular problem, the way that we're going to calculate the heat of the reaction is by using Hess's law. Hess's law says that we can take the heats or the enthalpies of formations of our products and subtract from that the enthalpies of formations of our reactants, and that's going to give us the overall enthalpy of the reaction. Products minus reactants multiplied by their stoichiometric coefficients. That's kind of the mantra. So I'm going to set up this delta H reaction calculation. Again, back up a little bit. We need the enthalpies of formations of all of these substances. The problem gives us the enthalpy of formation for the fuel. So that's going to be in this data table. And then for the other substances, the enthalpies of formation are in ALEKS's data tab. And I went ahead and copied them down here just to kind of make things a little bit easier. This is where the delta HF values are located, but you can find them in the data tab, or you can just look them up on the internet. Because ALEKS is providing the enthalpy of propane, and ALEKS sometimes can be a little tricky. This may actually be an incorrect number. ALEKS may just be giving this number. It may be right. It may be ALEKS has provided a funky version of the number just to make the problem even harder. So definitely take this number from the ALEKS data tab. Look or from the problem. Look the other numbers up in ALEKS's data tab or online. Okay, so set this up. Products minus reactants multiplied by their stoichiometric coefficients. Starting with CO2, the coefficient is 3. We're going to multiply 3 times the enthalpy of formation of CO2, and then we're going to add to that the same thing for our other product, water, multiply it by its stoichiometric coefficient, 4 times the enthalpy of formation of water. Products minus reactants, so moving on to the reactants. 1 times the enthalpy of formation of C3H8, and 5 times the enthalpy of formation of O2. So now we're ready to plug in the values that we have for each one of these. The enthalpy of formation of CO2, I've copied it down here from the data table. It is negative 393.5. I'm going to leave the units off for now just to kind of save space, but we'll bring the units back at the end. 4 times the enthalpy of formation of water, negative 241.8. I also left the states off in this equation, but all of these substances are in the gas phase. I left the states off again just to kind of save space. And then for our reactants, 1 times the enthalpy of formation of C3H8, that is negative 103.8. That's from our data table in the problem, negative 103.8. And the enthalpy of formation of O2 is just 0. And then let's go ahead and calculate this. 3 times negative 393.5 plus, I think I forgot a negative sign there, 4 times negative 241.8, 4 times negative 241.8 minus negative 103.8, and that gives us negative 2,043.9, and I'm going to bring those units back. Those units are kilojoules per mole. Now, I do want to take a minute here and talk a little bit more specifically about these units. These units, the way that we interpret that kilojoule per mole, this is a universal number that we can apply to any one of the substances in this equation. We're talking specifically about the propane in this problem. And so the way that we would interpret this number is that it is negative 2043.9 kilojoules for every 1 mole of propane. The reason that it is per 1 mole of propane is because that is the stoichiometric coefficient for propane. If this problem was asking us about, or if we were dealing with O2, then we would put a 5 down here because that's the stoichiometric coefficient for O2. If we were doing this for CO2, then we would put a 3 here because that's its stoichiometric coefficient, and you get the idea. So in your problem, if you do not have the same fuel as me, if you do not have C3H8 as your fuel, then it's possible that there might be a stoichiometric coefficient here, in which case you need to bring that stoichiometric coefficient down into this calculation for delta H. So what we have calculated is that every single time this reaction runs, we're producing approximately 2,000 kilojoules of heat for every 1 mole of C3H8. We do not have, in this problem, we do not have 1 mole of C3H8. We have 1 kilogram of C3H8. So what we need to do next is calculate how much heat we're actually going to evolve by burning all of this propane. What we want to do is multiply this by the actual numbers of actual amount of C3H8 that we have available to us in the problem. So our next step is to take this kilogram of propane, 1 kilogram of propane, figure out how many moles that is so that we can multiply this number by however many moles of propane we have, and that's going to give us the actual exact amount of kilojoules that are going to be released when all of this propane burns. So let's take a minute up here. I'm going to just kind of fit it in up here. Let's do a gram to mole conversion for the propane. I have 1 kilogram, multiply that by 1,000. I have 1,000 grams of propane, C3H8, and I want to do a gram to mole conversion. So that means I'm going to be using the molecular weight of propane, which is approximately 36 plus 8. It's approximately 44 grams. Don't approximate molecular weights on this problem. Take the time to calculate the exact molecular weight of propane, or just look it up on the internet. This problem, if you don't use the exact molecular weight, your answer is not going to be exactly right, and you're going to get it wrong. So don't be lazy like me, and definitely look up that molecular weight. 1,000 divided by 44 gives me 22.73 moles. So I have, in my 1 kilogram of propane, I have 22.73 moles of propane. I'm going to burn all 22.73 moles of propane, and that is going to give me way more than 2,000 kilojoules of heat. Remember, every 1 mole that burns is producing 2,000 kilojoules of heat, and I've got way more than 1 mole. So I'm multiplying this kilojoules per mole. I'm multiplying it by the exact number of moles that I have, and that is going to give me 2043.9. So this tells me that when I burn all of that propane, I'm going to be producing or releasing 46,452 kilojoules of heat. That's how much negative sign that means that it is being released. for the combustion of propane. So the problem is asking, we've done a lot of math here and we haven't even really started answering the problem. The problem is asking how many balloons can we blow up with this much heat? So the next thing that we need to figure out is how much heat does each balloon require in the inflation process? And that is going to be based on a couple of variables. That's going to be based on the size of the balloon and also how hot the balloon needs to get. And that information is coming out of the ALEKS problem. So the size of the balloon, this definitely varies from one problem to the next, but for this problem, I have 300 centimeter radius of my balloon. That is not going to be a useful unit. I'm definitely going to need to convert it to meters. So this is the size of my balloon. And then it's also telling me that the balloons, it says the air has a temperature of 25 degrees Celsius and it has to be heated to 100. So this is also important information. We know that we have to increase the temperature of the air by 75 degrees. Okay, so to help us do this calculation, we have the specific heat capacity of air. This means that we're going to be able to calculate the amount of heat using this Q-SMAT equation, QSM delta T. We're going to be able to calculate the amount of heat that is needed to blow up each balloon that is full of air. So we're going to be using the specific heat capacity of air, this number right here. We're going to be calculating the mass of air that's inside each balloon. And then this is going to be that temperature change. For us, it's 75 degrees C because we're going from 25 to 100. Yours may not be 75. Just pay attention to what those temperatures are. So this is the mass of the air. So what we need to do is figure out, we need to figure out how much air is inside each one of these balloons. And to help us figure that out, we have the density of the air. If we know the volume of the balloon, which we can calculate because we know the balloon's radius, if we know the volume of the balloon, we can use the density to figure out the mass of each one, the mass of air inside each one of those balloons. There is so much to do in this problem. Okay, so let's calculate the volume of each balloon. The balloons, it says, are spheres, and so the volume of a sphere is calculated with the equation 4/3 pi r cubed. The radius, we've been given the radius in centimeters. It's going to be helpful for us if we have the radius in units of meters because that's going to be consistent with the data that we have available to us in the problem. 300 centimeters is equal to 3 meters. To convert centimeters into meters, you just divide by 100. So this is 4/3 pi times 3 meters cubed. And we'll let the calculator do that. 4/3 times pi times 3 cubed, 27. Ooh. Is approximately 113.1 cubic meters per balloon. So that's the volume of the air inside the balloon. We need to know the mass of the air. The reason why we need to know the mass is because we need to use this Q-SMAT equation, and the Q-SMAT equation uses mass, not volume. So we're going to use the density to convert from volume, which is in cubic meters, into mass in kilograms. We're just going to multiply. Here's my density that I'm using right here. We're going to multiply our volume by the density, 0.946 kilograms per cubic meter. And 946. This gives me, my cubic meters cancel out, and this gives me a mass of 107 kilograms per balloon. So 107 kilograms of air per balloon. So now we know in our Q-SMAT equation, we know the mass of the air, we know the temperature change that is required, and we also know the specific heat capacity of the air because it's given to us in the problem. Now take a look at the units of specific heat capacity. The mass is in units of grams, and we're not going to be able to multiply grams times kilograms, so this mass of the balloon, or the air inside the balloon, 107 kilograms, we need to convert that into grams, multiply by 1,000. So we have 107,000 grams of air inside each balloon. We are ready to calculate the amount of heat that is required for each one of these balloons. This problem is so intense. 1.009 joules per gram degrees C, that's the specific heat. S, the mass of the air inside each balloon, 107,000 grams, and the temperature change required for each balloon is 75 degrees C. That's the difference between the starting temperature and the final temperature. And so that is going to give me 0.009 times my, I forgot to multiply. Forgot to 1.009 times 107,000. This problem fries my brain. Each balloon is going to need 8,097,225 joules of heat per balloon. That's a lot. This is joules. So again, let's take a minute to think about what are we doing. What we did was we calculated the amount of heat that was generated every time 1 mole of propane underwent combustion. We multiplied that number, that was this number right here. We multiplied it by the actual number of moles of propane that we have. And so we found that we have available to us a total of 46,452 kilojoules of heat. When all of our propane burns, this is how much heat is going to be released. Now we just calculated how much heat each individual balloon needs. That is in units of joules. We're comparing this number, the amount of heat that each balloon needs, to this number, the total heat that we have available to us. Notice that one's in joules and one is in kilojoules. So I'm going to take this joules, I'm going to divide by 1,000, and that's going to give me the amount of heat in kilojoules. So 8,097 kilojoules per balloon. Okay, so what did we just figure out? These are the numbers that we're comparing. We figured out with all of the propane that we have, we're going to release approximately 46,000 kilojoules of heat. Each balloon needs 8,000 kilojoules of heat. How many balloons can we blow up? That's going to be our total amount of heat divided by the heat needed per balloon. I have no more room to write that, so hopefully you can just follow along with that logic. 46,452 kilojoules of heat total available to us. Divide by each balloon needs 8,097 kilojoules of heat. This gives me, my calculator says, it's kind of faded there. I'm just going to have to write it out. I'm just going to have to erase some of this stuff. I'm going to erase this stuff right here. So my total amount of heat divided by the heat per balloon. I can't even spell. My brain is so scrambled. Per balloon. My total heat was 46,452. Don't worry about the negative signs, because remember, the negative signs are just giving us information about whether the heat is being evolved or whether the heat is being absorbed. Not important in this particular problem. We're just thinking about absolutes. Both of these are in units of kilojoules, and the calculator told me that is 5.74. So this is telling us that I have enough heat to blow up 5 balloons, not quite 6 balloons. The answer to this problem is going to be 5 balloons is how much I can blow up, not quite 6. This problem is so intense. It is so complicated. Take your time. Be patient with yourself. It is so hard. Make sure that you're double check all your math before you enter your answer into ALEKS, because this is not a problem that you want to have to do more than necessary.